Hi everyone, my name is Alex Walsiko Robert and I'm from Faculty of Engineering UMS and I'm under the supervision of Dr. Jidon Jenaun. Today I'm going to present my paper entitled The Oil Absorption Behavior of Natural Kapok Fiber as an Alternative to Commercial Synthetic Fiber. Alright, so we will start with a brief introduction of this paper. An oil spill contamination had become a main source of water pollutants, and it comes from various sources such as crude oil production, oil refinery, petrochemical industry, and restaurants. Dispersants, skimmers, oil booms, and solvents are some common methods that had been used to remove oil from water. Oil sorption by solvent has been identified as one of the most efficient and cost-effective methods due to its high cleanup efficiency. Researchers have found that kapok fiber demonstrates hydrophobic and oleophilic properties, high sorption capacity, oil recovery capability, retention capacity, and high reusability. There are three objectives of the study that we have managed to achieve. The first one is to evaluate the oil sorption capacity of kapok fiber. And the second one is to investigate the effect of NaOH treatment on oil sorption capacity of kapok fiber. And the third one is to determine the reusability of kapok fiber. And as you can see in figure 1, this is the kapok tree, and the fiber that we are investigating are the one in white color. So we will move to the methodology section. There are 4 experiments that has been conducted in this paper. The first one is the oil sorption capacity test for pure oil medium. The samples of raw kapok and polypropylene fiber are immersed 15 minutes in 2 pure oils. The first one is the 100% of used engine oil. The second one is the 100% of waste cooking oil. The sorption capacity test with pure oil was done to determine the maximum amount of the oil absorbed by the solvent. The oil sorption capacity test was calculated using the formula in equation 1 below. So this figure 2 showing that on the top one is the raw kapok fiber, and on 3 bottom one is the polypropylene fiber. And table 1 gather all the information of the characteristic of kapok fiber and the polypropylene fiber, and this was tabulated in this table 1 because we want to make a comparison between these two fiber before starting the study. The second experiment in this study is the effect of NaOH treatment concentration on kapok fiber oil sorption capacity. So according to a previous study by Wong et al. In 2012, a treatment concentration below 0.1 molar will boost maximum fiber's oil sorption capacity. Hence, in this study, the NaOH treatment concentration used was 0.02 molar to 0.1 molar, as we can see in figure 3. So 1 gram of raw kapok fiber was soaked in the working solution and left for 48 hours. And then the fiber was placed in 500 ml of distilled water with 1% of acetic acid to obtain the pH between 7 to 8 and left to dry overnight in 70-degree oven. And the effect of concentration of NaOH treatment on oil sorption capacity of treated kapok fiber was determined using the same formula in equation 1. The next experiment is the oil sorption capacity test for oil and water mixture. And various concentration of oil was added to a 500 ml of water to simulate an oil and water mixture medium. And then the fiber sample is immersed in the solution and taken out from the oil water mixture and left to drain for 5 minutes. A mechanical pressing of fiber was done to extract the oil water mixture from the fiber and placed in a 200 ml of N-hexane solvent. And after 15 to 20 minutes, the immersed fiber was taken and pressed again to extract all the remaining liquid. The extracted solvents were then poured into a separating funnel to separate water from hexane oil layer. The hexane oil mixture is then poured again into 250 ml round bottom flask and placed in a heating mantle, and distillation was carried out for 1 hour at 69 to 70 degree. The distilled liquid was placed in oven for 30 minutes at 90 degree to further evaporate any remaining N-hexane, and it is then placed in the desiccator overnight to allow the cool down process before weighing. Okay, this is the methodology for the reusability test. The sample of fiber weighing 1 gram is placed in a 400 ml of oil in a beaker. So after 5 minutes, the sample was allowed to drain for 1 minute and the final weight of the solvent was recorded. Then a vacuum filtration was used with a Bachner funnel to separate the oil from the solvent, as you can see in figure 4. And the test is repeated 6 times and the oil absorbency of the sample was evaluated. Okay, so we will move to the result and discussion section. For the oil sorption capacity test for pure oil medium, as you can see in figure 5, it shows that the RKF exhibited the highest sorption capacity compared to the polypropylene fiber for both waste cooking oil and also the used engine oil. The differences of the sorption capacity for both oils might due to the used engine oil has higher viscosity and density compared to the waste cooking oil. The lower sorption capacity of used engine oil is because more viscosity oil takes a longer time to saturate the fibers due to low rate of oil flow. And previous study also reported that the kapok fiber have strong adhesiveness to vegetable oil compared to the used motor oil, since waste cooking oil is a product of long chain fatty acids and ester, where used engine oil consists of aliphatic hydrocarbon. The results suggested that the raw kapok fiber has proven to exhibit higher sorption capacity compared to the polypropylene fiber. The effect of NaOH treatment concentration on kapok's fiber oil sorption capacity. As we can see in figure 6, the oil sorption capacity of treated kapok fiber at 0.02 molar of NaOH is the highest at 77.94 gram of oil, and the lowest at 0.10 molarity with 51 and 44 gram of oil. As shown in the figure 6, the oil sorption capacity of treated kapok fiber decreases as the concentration of NaOH concentration increases from 0.02 molarity to 0.1 molarity. And this might due to the alkalization process that removes the lignin, wax and natural oil layer from surface, which result in a rougher surface, which increases the binding sites for oil. The decrease of oil sorption capacity with increasing treatment concentration is related to the collapse of the rigid and hollow lumen. Previous study have found that high concentration of NaOH can cause the hollow lumen structure of kapok fiber to partly disappear, resulting in decrease in oil sorption capacity. Another study by Mukherjee in 1993 also found that the cellulose fibers treated with more than 1% of NaOH has poorer oil sorption capacity due to the weakening in fibers' solvent properties. Okay, so the oil sorption capacity test for oil and water mixture. As you can see, table 2 is the oil sorption capacity of raw kapok fiber and also the treated kapok fiber with waste cooking oil in water. Table 3 is the oil sorption capacity of raw kapok fiber and treated kapok fiber with used engine oil in water. The finding in this experiment suggested that the treated kapok fiber has a higher oil sorption capacity than the raw kapok fiber at highest concentration of oil, which indicates the treated kapok fiber has greater oil sorption capacity even at high concentration of oil in water. Furthermore, treated kapok fiber has higher oil recovery percentage and compared to the raw kapok fiber for all the concentration of oil and water used. In general, raw kapok fiber has more than 80% of oil recovery, which is lower than the treated kapok fiber that has oil recovery of mostly 90% and above. You can refer in table 2 and table 3. So based on table 2 and 3, a general trend of increased sorption capacity of raw kapok fiber and treated kapok fiber was observed as the concentration of oil in water increases. Other factors that affected the percentage recovery of oil from fiber could be due to the material handling during the experiment, such as the transfer of hexane oil water solvent from beaker to separator funnel to round bottom flask to be distilled. So for the reusability test, we can see in figure 7 the changes in oil sorption capacity of raw kapok fiber and treated kapok fiber for waste cooking oil and used engine oil after 6 cycles is tabulated in the figure 7. So based on the trend, it can be observed that the treated kapok fiber has better reusability compared to the raw kapok fiber. In terms of percentage reduction in oil sorption capacity, the treated kapok fiber decreased about 22.69%, whereas the raw kapok fiber decreased as much as 30.79% towards the waste cooking oil after 6 cycles. Simultaneously, the reduction percentage of treated kapok fiber oil sorption capacity is also lower towards the used engine oil compared to the raw kapok fiber after 6 cycles, which are 25.84% and 40.87% for the TKF and RKF respectively. So overall, the reduction in oil sorption capacity of kapok fiber are justified by the remnant oil trapped in the hollow lumen after each cycle and the deformation of the fiber structure. Excellent reusability of kapok fiber is beneficial to lower the cost of spill in oil treatment. As for the conclusion, oil sorption capacity for all fibers used in this study for both waste cooking oil and used engine oil medium are in the order of polypropylene fiber, raw kapok fiber, and followed by the treated kapok fiber in increasing order of oil sorption capacity. As the concentration of NaOH treatment increases, the oil sorption capacity of treated kapok fiber decreases. Hence, the optimum treatment concentration of NaOH concentration on kapok fiber was determined to be 0.02 molarity. So the treated kapok fiber has higher oil sorption capacity compared to raw kapok fiber towards the oil-water mixture for both waste cooking oil and used engine oil. Thus, the treated kapok fiber is a better recovery oil agent than the raw kapok fiber. In terms of the reusability, the treated kapok fiber is proven to have a better reusability compared to raw kapok fiber due to its lower percentage reduction of oil sorption capacity after 6 cycles compared to the raw kapok fiber in both waste cooking oil and used engine oil. So further researches on the application of the kapok fiber on real river water samples should be done prior to real life application of the kapok fiber. Alright, so these are all the acknowledgements of this study. The first one is the University Malaysia Sabah Innovation Grant Scheme, the University Malaysia Sabah Special Fund Scheme in 2019, and the third one is the University Malaysia Sabah Special Fund Scheme in 2021. And these are all the references. Okay, so that is all from me. Thank you very much for your attention. Bye bye.